Hello and welcome to lesson 9.2 arithmetic series. Today we're going to be defining what a series is and evaluating finite arithmetic series. A series is the expression of the sum of the terms of a sequence. And there's two types that we could have. And one being a finite series, which would be like 2, 4, 6, 8, all the way to like 28. That would be a finite series. It's finite because it has an ending point. I can see where I'm starting and I'm ending, and that happens to just be the sequence that it's adding up there is 2, 4, 6, 8, all the even numbers. An infinite one would look like, I'm going to do it in purple kind of below it, 2 plus 4 plus 6 plus 8 plus dot 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 forever. So you agree with me that that purple one, while it's infinite, would not be able to be summed up because 2 plus 4 plus 6 plus 8, as I keep going and going and going, it's just going to get bigger and bigger and bigger. Some infinite series will be able to be summed up. That's one of the big ideas that we're going to see over the next couple of lessons. So, big distinction here. Instead of a sequence, which I have commas between my numbers, which is just a list of numbers, here our series is adding up those numbers. It's the sum of all the terms of the sequence. And so instead of seeing commas between consecutive terms, I see addition. Sometimes you'll see subtraction if it's something that has negative values, or if it has where it alternates from positive to negative, you'll see a plus and a minus, plus and a minus. So those are our two types of series, finite series and infinite series. Now, I asked you to start this lesson by thinking about how would you add up all of the numbers from 1 to 100. Okay, but I said don't just add them up on the calculator because that's a waste of time to say 1 plus 2 plus 3 plus 4 and type it all the way into 100. But if we think about that, 1 plus 2 plus 3 plus 4 dot, 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 all the way to, I'll say like 98. Sorry, my stylus broke, so I'm working with my finger. It's not writing very well. All the way to 100. Okay, so this is an example of a finite arithmetic sequence. It's arithmetic because my common difference here is 1. I'm increasing by 1 between consecutive terms. I'm adding up the terms of that sequence, and so it's arithmetic sequence. Now, how I would do this is I would take this same sequence again, and so if I do the same series again and just write it the other direction, I don't know why. 100 plus 99 plus 98 plus 3 plus 2 plus 4. And again, there's a couple of different ways to do this. Some people say add the first and the last, add the next two, next two. I'm just adding the same series again, the other direction. So now I have it descending, and when I tally these up together, 1 plus 100 is 101, plus another 101, plus another 101, plus all the way, and every single one of these numbers is going to be 101. I know, pretty snazzy. So, of these, there are 100 terms like this. So I have 100 times 101, but I have it there twice. So I'm going to divide by 2 to find what that actual sum was, which is 50 times 1, which is 5,000, which is 5,050. So back to an arithmetic series, which this really was an arithmetic series. An arithmetic series is the sum of the terms of an arithmetic sequence. So again, I'm adding up all of those consecutive terms. The formula is given when I have n terms is given by dun, 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 the sum is equal to the number of terms times AF plus AL all over 2. When I'm referring to this AF and AL, AF is my first term, and AL is my last term. Sometimes you see them listed as A1 and AN. I'm not a big fan of listing it as A1 because not every single series is going to start on the first term. Sometimes they start on the 10th term, or sometimes they start on the 15th term, or sometimes they start on the 0th term. So I'm not a big fan of using A1 and AN there, but some textbooks do and some resources do, so just as a point of reference. Seems vaguely familiar. Let's look back to that problem we just did. The number of terms that I'm summing up times the sum of the terms AF plus AL over 2. So I just kind of informally showed you where that formula, a way we can think of where that formula is coming from. Just another moment with it. Make sure that you get it jotted down if you have not already. Okay, so evaluate the following series for S12. So this one has this little 12 subscript there. And so that's referring to summing up the first 12 terms. Okay, so things that I need. Well, I know my N is going to be 12. I'm a big fan of making a key for these. My AF, my first term, is 0.17. And my AL, that's going to be A12. Unfortunately, with the list that they gave us, it doesn't go all the way out to the 12th term. So I'm going to have to find that. So here's where our arithmetic sequences come into play. So arithmetic series and arithmetic sequences, we need that background knowledge here. So AN is A1 plus T times N minus 1. That's our arithmetic sequence formula, which is really just plain sum. How funny is that? AN is 0.17. Our common difference here, our common difference is negative 0.04 and minus 1. So then when I want to find A12, I have 0.17 minus 0.04 times 11, 12 minus 1, which comes out as negative 0.27. I should put the zeros on there. So now that I have what A12 is, or that last term, that's my AL, and I wrote A12, AL on that, I can do my sum. So my sum of the first 12 terms, so that little subscript's referring to the first 12 terms, is 12, 0.17 minus 0.27 all over 2. So 12, 2, which is Alright, so let's take a look at another one. We can also write them in this sigma notation. So this is my arithmetic sequence that I have, and I'm starting from the first term and I'm going to the 16th term. And it is possible to write out all 16 terms and then add them up, but we can actually use the arithmetic series formula, which is what we're going to do now. So if I'm going from the first term to the 16th term, that's going to be a total of 16 terms. My A1, that's my first term, and that's from down here on the bottom. And then the other part that I need to know is A16 from the top. So when I want to find A1 and A16, I'm going to take those numbers and plug them in for the N. Right there. Negative 52 for that one. And when I take that one in, I'm going to have 8. I don't know why it switched pen color or something, but whatever. Doesn't really matter. The purple's lovely anyway. Okay, so there's my N, my first term, my last term, and now I'm going to do the sum formula. space. So I have my sum is equal to 16, 8 minus 52 over 2. So comes out as negative 352. This one's a little trickier. Take a minute, pause the video, and try it. But it does have a little twist on it. Did you try it? I hope so. So my AF is going to be A20. My AL is going to be A40. So A20 is negative 51. A40 is negative 111. Now the tricky bit is N. N here, you want to say it, some people want to jump to it being 20 or 40 or things like that. So we want to think about, I'm ending on this term and I'm starting on this term. So I have the 20th term, 21st, 22nd, 23rd, 24th, 25th, 26th, 27th, 28th, 29th, 30th, 31, 32nd, 33rd, 34th, 35th, 36th, 37th, 38th, 39th, and 40th. That's 21 terms. You do not want to use this bottom number. You do not want to subtract them. Well, you could subtract them and then add 1 back, because you think back to here, it was kind of just this number on the top, but if I subtracted it, 16 minus 1, that'd be 15. It wouldn't be right. So it's like top minus bottom plus 1. Okay. So now I'm going to take my pieces and put them in my formula. So type in correctly, it comes out as negative 1,701. Pretty good on these? Take a minute, pause the video, and try this one on your own. So we need to find A5. It's going to be negative 2. We need A17. 17 minus 7 is 10. And my number of terms here is 13. It's not 12. I always have to, you're adding 1 to include that starting term at the bottom as well. So negative 2 plus 10 over 2. Should be 52. Yeah, 52. And this is what the sum is. Notice here on my S's, I'm not writing a subscript because I'm not doing, 52 is not the sum of the first 17 terms. It's the sum from the 5th term to the 17th term. So it just doesn't get a subscript anymore. You just write an S. Ooh, tricky, tricky, tricky. Find an expression. So we're not going to have a numerical answer here. Our answer is going to have x's in it. For S12 of this sequence, 5x squared, 7x squared, 12x squared. So my AN is going to be my A1. My common difference here is 5x squared times n minus 1. So I'm writing my explicit formula first. Then I'm going to find my AF, that's A1 really here. And then I need my last term, which is going to be on the 12th term, because that's from right here. That's going to be 2x squared plus 5x squared times 11. 12 minus 1 is 11. I have 55x squared plus another 2x squared, so 57x squared. And if I'm starting at the first term and going to the 12th term, that's going to be 12 terms in total. So when I do the sum of the first 12 terms, it's going to be 12 AF plus AL over 2. More space. Oh, 59x squared. So the x squared really didn't do anything. It didn't change anything about how I'm doing this problem. So don't be intimidated when you see if you see a problem that has variables in it as well. There's nothing to be afraid of. We'll work with it exactly the same way. Go ahead and try this one. You paused it and tried it, right? All right, so again, I'm doing the first 12 terms. My AF for my first term is x plus 9. Still need to find my AL, or my 12th term. So AN is the first term. What's my common ratio here? How much am I adding to get to there? Well, I'm adding a positive 2x and a negative 4 between consecutive terms. When I want to find A12, we're going to go x plus 9 plus 2x minus 4 times x plus 9 is 22x minus 23x and minus 3. That's my last term. I still need to find my sum though. So my sum of the first 12 terms is going to be 12. My first term plus my last term all over 2. I'm going to simplify the 12 over 2 is 6. Didn't have to do it that way. I think it's easier. How my brain is processing. 144x minus 156. So that's the sum of the first 12 terms. Additionally, we can look at these with word problems as well. So a theater has 30 seats in the first row of the center section. Each row behind the first row gains 2 additional seats. So there's your common difference. And there are 20 rows in total. So I have a common difference of 2. I have a starting one of 30 because there's 30 seats in that first row. Okay. So how many seats are in the 20th row in the center section? It's only the center section in this whole problem. So that's the fact that we're having it in the center section has no period on it. Well, that's a term number. So I want to find our explicit formula first. So 30 plus 2 times n minus 1. So in the 20th row, I'm going to have 30 plus 2 times 29. Oh, 19. See, I'm getting tired. I apologize. So 19 times 2 plus 30. There are 68 seats in that back row. Now, how many seats are in the entire section? That's our 20th of the sum of the first 20 terms, or the first 20 rows. It would be 20 terms. The first row has 30. The last row we just figured out had 68. And I have it over 2. Since 20 is divisible by 2, I'm just going to go straight to 10 there to make my problem easier. 30 plus 68 is 98. Times 10 is there's 980 seats in the section. Pretty good? Another word problem, application problem. All right. So a construction company will be fined for each day it is late completing its current project. The daily fine will be 4,000 the first day. Yikes. And will increase by 1,000 each day. So there's how it's arithmetic. It's increasing by 1,000. So the first day it's 4,000, then it's 5,000, then it's 6,000, then 7,000, etc. Okay. Based on its budget, the company can only afford $60,000 in total fines. What is the maximum number of days it can be late? This is going backwards than what we've been doing. So the previous problem was like, here are the outputs, tell me the total. Here I'm telling you, here's the total we can have, what must have been the outputs. A little bit different. So start by writing the explicit formula. It's 1,000 for that A1. Oh, no, 4,000 for that A1 plus 1,000 per day. Now, I'm actually going to take this and simplify it. I don't usually bother, but because I'm going to have to solve backwards on this, I want to have it as simplified as possible. So this is 3,000 plus 1,000n. Okay, are we all right with that? I just distributed, combined like terms, and went from there. So we don't know what our n is, and I'm not going to know what my last term is as well. But I do know my first term is 4,000. Okay, so I'm going to have 60,000. And if you were really clever, you could probably do this whole problem in terms of thousands and have it be 60 on this side and it'd be a lot nicer looking. But I've committed. My n times the sum of my first term plus my last term. But I don't know my last term. That's what you're saying, right? You're like, Ms. Marhefke, we don't know the last term. How are you going to do that? I'm going to just write it in terms of n. 3,000, because I don't know what this n is either, plus 1,000n. And then I'm going to put that all over too. Oh, 6,000 and 7,000 plus 1,000 and all over 2. This is creating a quadratic that I'm going to be able to solve. Isn't it wonderful that we did quadratics earlier this year so I can make this connection right now? I know you think it is. So I'm multiplying, I should have written that in, hold on. I'm going to multiply both sides by 2. I kind of just was going, I apologize. And that'll cancel this 2 in the denominator, and then it'll make it easier to solve. And then I'm also going to distribute. I'm being wild and doing 2 things at once. I know. Crazy. All right. I'm going to divide by 1,000. I mentioned it before. You could do it at pretty much any point, but I'm tired of it now. So much better looking, right? I'm going to get everything onto one side. And then at that point, I can use one of my strategies for solving a quadratic. So I could solve by factoring. I could solve by completing the square. And I'm not going to solve by completing the square, but I could if I wanted to. Or I could use the quadratic formula. So I'm going to factor, because that's how I roll. N plus 15 and n minus 8. So obviously one of these answers does not make sense, and one does. So n is either negative 15, nope, or positive 8. We can't have a negative number of terms because that would be that they had a negative number of days that they were late on something, and that doesn't make any sense. So here instead we're going to say that n is 8. So they could be late 8 days, no more than that. So they better get to work and spend less time calculating how long they could be late and actually doing the job. All right, and this concludes our lesson on arithmetic series. We have met our objective. We evaluated finite arithmetic sums. We did them forwards, we did them backwards, we did them with variables, we did them with numbers. And as a reminder, just as a closing remark, the formula, in case you haven't internalized it yet, is S is equal to N times the sum of, or the quantity of, AF plus AL all over 2, where AF is representing the first term, AL is representing the last term. And sometimes that first term is A1, and sometimes it isn't. All right, have a wonderful day.